Hello students, good morning all of you. Today in our video I want to explain moving charges and magnetism. So this is our new chapter and it is very important for IIT JEE and NEET. Okay, so before going to learn you have to subscribe my channel and like, share to your friends. Okay, let us start our topic. Moving charges and magnetism. Moving charges and magnetism. So here, moving charge. What is a moving charge? So moving charge, it is nothing but current. Moving charge, it is nothing but current. Flow of electrons, right? So here it is magnetism. So it means a current carrying conductor carrying wire behaves as magnet. So a current carrying wire behaves as magnet. Very important point. So this is the one of the observation by the scientist name, it is Oersted. Observation by the scientist name Oersted. So what is that observation? A current carrying conductor behaves like as a magnet. A current carrying conductor behaves like as a magnet, and a current carrying conductor can be produces magnetic field around itself. This is a current carrying conductor. It can be produces magnetic field around itself. How he can observe? So first suppose this is a one of the wire having current I. When he kept a compass needle near to the current carrying conductor, this is compass needle near to the current carrying conductor, then he observed that the needle in the compass needle, the magnet should be deflects. The deflection should be, he was observed deflections. And this is the first observation of the Oersted, the scientist named Oersted. And then after we are studying by the combination of moving charges and magnetism. Before that, magnetism is a separate topic, and moving charges, it means current or current electricity, that is another separation. Clear? Whenever he observed this type of observation, then the science, the electrostatics and magnetism will be combined to each other, and he defined the electric current carrying conductor. It can be produces magnetic field around itself. So, and he observed he can changes the direction of the current in a conductor. So this is a change in direction of the conductor due to this. So, and then the compass needle also changes its deflections. So here we have to observe in which direction the current will be there. In that direction, the magnetic field was produces. That's why he concluded that the current carrying conductor produces magnetic field around itself. So this is the main theme you have to study, moving charges and magnetism, right? By the experiments of Oersted. You should not do this type of experiments in the room. So where the scientific observation or supervision, then only you have to do this type of experiments. Okay, right. So coming to the direction of the current and to the magnetic field, if they can be changes by the direction of the current will be changes, the deflections of the magnetic needle also changes. Okay, so in this, regarding in this, we have to practice some more laws in the moving charges. Okay, if a charge is kept nearer to the, if a charge q is kept nearer to the current carrying conductor which is at rest, then no forces acts on it, okay. If there is a conductor, current carrying conductor or current carrying wire, and we have to kept nearer it, there is a charge q which is moving with velocity v, then it can be deflects with some angle, that is the forces should be acts on it. So which type of forces acts on it? That is the due to the magnetic field. Due to the magnetic field, the force should be acts due to the magnetic field. Okay. And if there is a magnetic field, so this is the magnetic field here, or electric field. If it is a electric field, if there is a charge which is at rest or which is in moving or motion, then this is the electric field. Okay, in that electric field there may be a charge will be kept in that field, then the force should be acts on that. F is equal EQ. Here we have to remember the charge either rest or motion. Charge either rest or in motion. Okay, here the velocity, it is not applicable, as of course it has constant velocity or variable velocity. Whatever the velocity, it is not that matter, it moves some velocity. Whenever the charge was moving which is nearer to the electric current carrying conductor, then the forces should be acting on that charge. That forces are acting due to the magnetic field. And here there is a charge which is at rest, it cannot be moves. And then there is a current carrying conductor, but there is no forces will be acting on it. Okay, this is the points you have to observe, right? So now we have to see about the one of the observation of the magnetic field by the scientist named Biot-Savart. So Biot-Savart, Biot-Savart law. Right? What is the Biot-Savart law? If there is a infinite charge carrying conductor, infinite current carrying conductor, and this is the current carrying conductor, and from this there may be a point P here, So the length of the current carrying conductor, it is, let it be infinite, okay, or maybe a L length of the current carrying conductor. So here we have to assume that some small element, that is dl, from this point to the point P is at there in the distance of r, in the distance of r. The angle made by the dl and r, it is the theta. The angle made by the dl and r, it is the theta. So here, to find the magnetic field here, that is the dB, it is equal to dB, it is the magnetic field acts at the point P by the dl element. By the dl element, it is dB is equal to mu naught by 4 pi I dl cross r. These are the vector form by r cube, dl cross r by r cube. So this is the vector, okay. And here in the scalar quantities, we can write dB, it is equal to mu naught by 4 pi, whereas I dl r sin theta by r cube, because of a cross b is equal ab sin theta. From a cross b is equal to ab sin theta, as you can write that dl cross r, it is equal to dl r sin theta, where dl r sin theta, r and square will be cancelled, then dB is equal to mu naught by 4 pi I dl sin theta by r square. So this is the magnetic field acts at the point which is in r distance by the dl length of element, okay. So this is the scalar. So this is the vector form and this is the scalar form of magnetic field, okay. Straight wire, okay, okay. From this you can write that where dB is directly proportional to the current passing through the conductor and dB is directly proportional to the length of the small element, okay, and dB is directly proportional to the angle of sine, that is sin theta, and it is inversely proportional to the square distance between them. So here mu naught, it is the permeability of free space, it is vacuum or whatever, permeability of free space, okay. And the value of mu naught by 4 pi, it is equal to 10 to the power minus 7, So here the units of dB, it is equal Tesla. dB, it is in Tesla. Units of dB, it is Tesla, or it may be Newton per ampere meter. These are the units of the dB, okay. From the flux, magnetic flux, you can write that what is magnetic flux? B dot A, right? B, it is equal phi by A, right? Phi, it is the flux, it has Weber, by area, it is the meter square. Weber per meter square also, units of the flux, Weber per meter square also. So Weber per meter square and Newton per ampere and Tesla. So these are the units for the magnetic field, okay. So this is the Biot-Savart law. So due to the Biot-Savart law, the magnetic field at a point P, which is at r distance of dl element, is directly proportional to the current passing through the conductor and also directly proportional to the length of the small element and directly proportional to the angle of sine between dl and r, between dl comma r. Okay, and also it is inversely proportional to the square distance between them. So this is the Biot-Savart law. So now here we have to remember one thing. The direction of the dl is always the direction of the dl. dl is always in the direction of current. dl is always in the direction of current because of in we have to current carrying conductor, we are assuming a point that is dl. So what the direction has the wire, that direction has the small element. So this Biot-Savart law is applicable only for the, it is applicable for small element, small elementals. Okay, small elements. It means small length of particles, small length of parts, right? Okay, the main thing you have to learn here, that is the direction of the magnetic field. The direction of the magnetic field. So how we can measure the direction of the magnetic field? Let us see. Very important basic standards for to find the direction of the magnetic field. So it is a direction of magnetic field. This is a current carrying conductor I. This is the small element dl. Distance of r, there is a point P. Here the dp, the direction of the dp. So here this is the dl and this is the r. The direction of the point P, it is the, here the direction of the current carrying conductor from the r distance, that point where we have to locate P. The direction at this point of magnetic field dp, it is equal inward. Okay, so from the screw rule, from the screw rule means, if you have, whenever you have to tighten the screw with in the clockwise direction, we have to turn the screw with the clockwise direction. So then it will be, so this is a screw and we have to turn in right in this direction, right? So then it will be inwards. So the inward means we have to keep this sign. This is the inward. When by the screw law in the clockwise direction, clockwise. Okay. If there is a point P here, so this is the dl and here there is a point P in the r distance. So this is the magnetic field at this point. It is dp is equal outward. So this is the outward. Outward means in the screw we have to turn it in the anti-clockwise direction. In this direction it will be comes like this. Okay. So inward means in the clockwise direction. So here, so this is the clockwise direction, then it will be penetrates, it means inward. It will be in the anti-clockwise direction, so it will be come outside, that is outward. Outward will be denoted by this symbol and inward should be denoted by this symbol. Here the best method you have to remember, that is right hand thumb rule. Right hand thumb rule. So what is the right hand thumb rule? So the right hand thumb rule, it is, here there is a current carrying conductor, which this is the right hand, the thumb should be as like this, the direction of the current, and this can be called, that is the magnetic field. For suppose here there is a point P, at this point we have to find the magnetic field, then the magnetic field at this point dB, it is equal. So when we have to put your thumb in this direction and your fingers are curled around the wire, then it should be inwards. So here this is the direction of the magnetic field. Okay, if there is a point here, seen somewhere, so this is the current carrying conductor, has current passing I, and from the DL element there is a point which you have to select at this point P in your distance. So by the right hand thumb rule, this is your right hand thumb, and this is your fingers, and it may be in this side. So this is the thumb here, and these are the fingers which are curled. So this is outward. So here dB, it is equal to outward. Outward means you have to keep this side outward and this is inward. So this is the best trick you have to use, as we have to find the dB value. So here one more thing you have to find. Remember, dB is always perpendicular to the dB is perpendicular to DL and dB is perpendicular to R. Okay, so D perpendicular to the DL and R. It means you have to remember these two. dB is perpendicular to the DL value and dB is perpendicular to the R value. Okay, right? So this is the points you have to remember. So whenever you have to keep this right hand thumb and your fingers are curled, this shows the inward and this shows the outward. Okay, first suppose let us see one more example. Here there is a current carrying conductor I. There is a point P. At this point, what is the dB value, right? And at this point Q, what is the dB value? What is the direction of dB? Right? So let us see. So this is your right hand thumb, and you should keep this as in this direction. This is your thumb, and it will be inward. Your fingers are like this, right? Your fingers are like this. So that is inward. The direction of dB is here inward. Coming to this point, so this is the direction of the current, and you have to put your thumb, and this is the point P and this is point Q, this one. So now this is the right hand thumb, these are the curls. It means, so here the direction of the magnetic field is outward. So this is the process you have to clearly, easily find out. So this is the inward. Okay, very simple, right? The field, magnetic field due to finite charge, finite current carrying conductor, current carrying conductor. Okay, so magnetic field due to finite current carrying conductor. So here this is a finite current carrying conductor, so which is current passing this is I. Okay, so at anywhere of this in a perpendicularly you have to take a point in a perpendicular distance of A. There is a point you have to choose. At this point you have to find the magnetic field. At this point you have to find the magnetic field, right? From this point, from this we have to write right. So here this is the angle of phi 1 and angle of phi 2, angle of phi 1 and angle of phi 2. Okay, and here this contains how much angle it is, 90 degrees, because of we have to take in perpendicularly, right? Here there is a point which is having the length of L, which you can assume dl element. So here the distance it is r, in r distance. Okay, so we need to find that the magnetic field due to finite current carrying conductor by the dl element, magnetic field due to conductor by dl length of element, right? So that is dp, it is equal to, you can write that mu naught by 4 pi I dl sin theta by r square, ideal sin theta by r square. Here just you have to find, so theta where it is, which is makes an r, this is the theta, you have to remember, right? So this is the phi 2 and this is the theta, and here to get for getting the total magnetic field you have to integrate on both sides, that is dp, it is equal to integral of mu naught by 4 pi where ideal sin theta by r square. So here we should not do the integration because of there is no d theta, this is only sin theta. Whenever there is a d theta, then only we have to, okay, you have to do the integration process. So let us find R value and DL value here. So from this one we have to, from this one means where is, this is point A and this is point B here. Okay, this is the one of the right angle triangle, right, APB. Okay, so in this we have to find the cos theta value. Cos theta, it is equal, what is cos theta here? Opposite by, sorry, adjacent by hypotenuse, that is A by R. Here you can write R, it is equal, what is that? A by cos theta. A by cos theta. This is the point you have to remember. R is equal to A by cos theta. Where R square, you can write that R square is equal to A square by cos square theta. It is fine. And you have to find the theta value. So how you can find the theta value? In this, you have to find theta or DL value. You have to find the DL value. Here there is a L. L, it is the opposite side. So then tan theta from this triangle, tan theta, it is equal to, what is that? L by A, opposite by adjacent. Okay, L, it is equal to A tan theta, right? DL by d theta, it is equal, DL by d theta is equal, here you can write that A into secant square theta, secant square theta. DL by d theta is equal secant square theta. This is one of the point you have to remember here. DL by d theta is equal secant square theta. From this you can write DL, it is equal, what is DL here? DL is equal A secant square theta d theta. A secant square theta d theta. Okay, A secant square theta d theta. So let us substitute all the values which are in this equation. The limits, you have to find the limits also. The limit is at this point, so this is the one of the limit and this is the one of the limit. In upper side you have to take positive sign, in lower side you have to take negative sign. So that is, you can get the capital B value where you have to get integration, and then integral of minus phi by 2 and plus phi 1. Minus phi by 2 and plus phi 1, where it is mu naught by 4 pi I into, what is DL here? DL nothing but A secant square theta d theta. A secant square theta d theta, right? By, what is that? R square? R square is equal to A square by cos square theta. A square by cos square theta, right? So here 1 by cos square theta is equal secant square theta. Secant square theta and secant square theta cancelled out. So here this one and this one gets cancelled. In that A square, the square and A will be cancelled out. So what is remain here? So this is mu naught by 4 pi and it is I by A integral of minus phi by 2 phi 2 and it is phi 1, where it is, what is that? D theta. Here what is that here? That is only 1 into d theta. 1 into d theta here. Okay, so that is, you can get, sorry, secant square theta is there, it is sin theta also, is there here sin theta also. Okay, from this DL sin theta, DL into sin theta. So here you can write sin theta into d theta, sin theta into d theta, right? So here the theta value, how much the theta it is equal to? Theta it is equal from this point, where theta it is equal, how much it is? If it is 90 degrees, at this theta value, you can find it is 90, where it is 90 minus theta, Let here it is mu naught by 4 pi I by a integral of minus phi by 2, phi 2 and phi 1, where it is sine 90 minus theta into d theta, right? Sine 90 minus theta, okay? Sine 90 minus theta, it is equal cos theta. You can write integral of cos theta, it is nothing but sine theta. Again, it can be given to us sine theta here, okay? Therefore, you can write here B is equal mu naught by 4 pi I by a integral of minus phi 2 phi 1 cos theta d theta. Integral of cos theta d theta is equal sin theta. Mu naught by 4 pi I by a, it is sin theta, limits of minus phi to phi 1. Now let us substitute the limits. Applying the limits, mu naught by 4 pi I by a, whereas sin phi 1 minus of minus sin phi by 2, minus into minus plus, there is sin phi 2. So here this is the intensity of the, this is the magnetic field where we have to find the finite current carrying conductor. B is equal to mu naught by 4 pi I by a sin phi 1 plus sin phi by 2, phi 2, sin phi 1 plus sin phi 2. Very important. So here B is equal, how much it is? Here B is equal, the answer it is mu naught by 4 pi I by a sin phi 1 plus sin phi 2, right? So these sin phi 1 and phi 2 are the opposite angles here. This is upper side and this is lower side. So here this is the phi 1 and here this is the phi 2. These are the opposite to each other, right? You should keep the value of mu naught by 4 pi always as mu naught by 4 pi. You should not cancel any value by the 4, because of it can be difficult to calculate the numericals. So already know mu naught by 4 pi it is equal, mu naught by 4 pi is equal 10 to the power minus 7. If you can get the mu naught value, it is 4 pi into 10 to the power minus 7. So it may be useful to calculate as easy, right? So this is the magnetic field due to finite current carrying conductor. Very, very important. So what we have to do here, that is, we can find the magnetic field which is at the point P, at the point. So this point is not at just you have to take at the midpoint, or it is whatever the point you have to take in here. You should not, there is no rule to take as midpoint, or it is starting point, or it is final point. Not at all a matter. You can find, you can choose the point which is perpendicular to the current carrying conductor, which is perpendicular to the current carrying conductor. That is the rule. Okay. So here A it is the perpendicular distance and I it is the current passing through the conductor, and phi 1, phi 2 are the angles made by the point P. Mu naught by 4 pi is the constant, that is 10 power minus 7, right? Okay. So here let us see some numericals. The question it is, I it is equal to 2 ampere and R it is equal to 10 meter. right? Phi 1 it is equal 45 degree, phi 2 is equal 30 degree. Find magnetic field of a finite current conductor, current wire, right? So here this is a finite current carrying wire which is having I it is equal to 2 ampere, and the distance, perpendicular distance A it is equal to 10 meter here, and the point P, at this point you can find where it is. Phi 1 it is 45 degree and it is 30 degree, right? Find the dP value here, right? So dP is equal to mu naught by 4 pi, you have to find the B value. Mu naught by 4 pi I by A into sine phi 1 plus sine phi 2. So this is the formula here, where mu naught by 4 pi 2 by A is equal to 10. A is equal to 10 meter, I is equal to 2 ampere into sine 45 plus sine 30 degree, where it is mu naught by 4 pi 1 by 5, okay, into sine 45 1 by root 2 plus sine 30 1 by 2 of Tesla. So you have to simplify this, you can get the answer. Okay, so this is the method you have to find the magnetic field of a finite current carrying wire or a conductor, right? Let us see one more. There is a square of a side A. So this is current carrying, right, at the point center of the point, at center point P. So find the magnetic field at the center point P of a square sides of A. Square sides of A. So each side has length A, right? Each side has length A. So at this point you have to find the dB value. It means magnetic field. So you can draw the perpendicular distance of A. So here this is A, total distance is A, and from this point, this is the center point, it is A by 2 here. Clear? And you can draw these two angles. So this one and this one. So here this is 90 degree. This is the square, that is, you can write here 45, and this is also 45 degrees. Okay, and this is 45 degrees. So from this you can write that phi 1 is equal 45 degree and phi 2 is equal 45 degree, and A it is equal to A by 2. Okay, you just find B value. P is equal to mu naught by 4 pi here. This is one side I have to choose in. Just B1. Let it be B1 here and B2 here from this point. So here there is, from this point here there is. So this is B3 here and this is B4 here. Okay. So I have to find one point, and this is a square. I have to multiply by the how many wires are there, that much of time I have to multiply that. Mu naught by 4 pi I by A sine phi 1 plus sine phi 2. Okay, let B1 is equal mu naught by 4 pi I by A means A by 2. It is sin phi 1, it is sin 45 plus sin 45. Okay, so that is mu naught by 4 pi 2i by A, 2i by A to 1 by root 2 plus 1 by root 2. Okay, so then it is equal mu naught by 4 pi 2i by A, it is 2 by root 2. 1 by root 2 plus 1 by root 2. Root 2 is LCM and 1 plus 1 2 are 2 1 by root 2's. Okay, so then you can write it is mu naught by 4 pi 4i by 2 into 2 are 2 2 are 4i by A root 2. Right, so this is the B1 value. The net field, net magnetic field is equal to B1 plus B2 plus B3 plus B4. So how many wires are there? 1, 2, 3, 4. And then it is 4 into B1, 4 into B. B net is equal. So 4 into, what is B here? Mu naught by 4 pi, right? 4i by A root 2. So then 4 into 4, it is 16. Mu naught by 4 pi, it is 16i by A root 2. So this is the net magnetic field acts on the point centroid at P, which is of a square sides A. Okay, so this is very important. You have to find the magnetic field of a square. Let us trying for the triangle also. Equilateral triangle. Here there is a equilateral triangle of length L. Okay, at the centroid P, find magnetic field at magnetic field of 3 wires. 3 wires. So there are 3 wires are there having current I. So let you have to take the triangle as here. So here this is the one of the equilateral triangle, as the current passing here, this one of length it is L here, right? At this point, center point, where is a P. So here this is the perpendicular distance, that is nothing but let A. At this point, so here you have to write the angle where this one and this one. So here this is 90 degrees, already you know that, perpendicular, and here for the equilateral triangle there is 60, and then here 30 degrees, here 60 degrees. So here phi 1 is equal to 60, phi 2 is equal to 60, right? You can measure the perpendicular distance. Perpendicular distance is the angle to the opposite, where you can find tan 30, it is equal to, what is that? A by opposite by adjacent. Adjacent, how much it is? Here it is L by 2 and it is L by 2. Here it is L by 2. Right? So here you can write that, where tan 30 it is equal root 3 by 2 and then 2a by L here. Right? 2a by L. So here you can write where tan 30 is equal to 1 by root 3, it is 2a by L here. A it is equal L by 2 root 3. L by 2 root 3. So this is the perpendicular distance here. Clear? And then the formula it is mu naught by 4 pi I by A sine, what is that, 60 plus sine 60, right? So here we have to substitute here mu naught by 4 pi, where I by L by 2 root 3, it is 2 root 3 here, right, into sine 60, it is equal root 3 by 2 and plus root 3 by 2. Okay, here it is equal mu naught by 4 pi I by, this is only one side I have to find, I into 2 root 3 by L into root 3 by 2 into 2 root 3 by 2, 2 root 3 by 2 here. So this 2 will be cancelled out, and then you can find mu naught by 4 pi, it is I into 2 root 3 by L. So 2 root 3 into root 3 here, 2 root 3 into root 3, 2 root 3 into root 3 into root 3 is equal 3, 2 into 3 is equal 6, so therefore it is B1. So B1 is equal to, you can write B1 is equal mu naught by 4 pi 6I, because of root 3 into root 3 3 and 2 into 3 6, I by L here. Okay, so this is B1. So B net it is equal to B1 plus B2 plus B3, because of here in equilateral triangle there are 3 sides are there. This is B1 and B2 and B3 here. Okay, so this is ABC equilateral triangle. So here 3 into B here, what I am going to find B. So here 3 into, it means 3 into mu naught by 4 pi 6I by L. It is mu naught by 4 pi 18I by L here, 18I by L here. So this is the net magnetic field by the equilateral triangle. Net magnetic field by the equilateral triangle. Okay. Let us see one more, which is the last one. So here there is a current carrying conductor I. From the center of this conductor at the distance of A, we have to assume a point P. So here you have to find the magnetic field, which is length of the conductor is L. Length of the conductor is L. Okay. So here, so B it is equal to mu naught by 4 pi I by A into sine phi 1 plus sine phi by phi 2. Phi 2. Here, what is the phi 1 value here? Phi 1 it is equal. So perpendicular distance, that is equal to A, which is on the along with the line of current carrying conductor. So that is equal to 0 degree here, because of these two lines are in parallel, and also phi 2 is also here 0 degree. Phi 2 is also here 0 degree. So then we can calculate here mu naught by 4 pi I by A sine 0 plus sine 0. Sine 0 is equal 0. Therefore, something into 0, it is equal 0. So here this is the magnetic field, B is equal 0. So you can say here the magnetic field along so the magnetic field along with the wire is always 0, right? So here this is the method you have to find the magnetic field of a current carrying conductor at any point. Clear? So if you like this video, please subscribe my channel and share to your friends. And if you have any doubt, you have to comment in comment section. I will be explaining all of your doubts. Thank you.